Okay, welcome. Lesson 5, the languages part. We're going to start by looking at the finite state automaton as we did the previous lesson. So if we have a finite state automaton called M, this M is defined by several elements. So the first element here is the alphabet. So what kind of symbols can be entered into this finite state automaton? And the second one was the possible states. And hopefully you remember that this one were the accepting states. So when can a word be finalized? Then we had to have an initial state, in this case S2, and we have a state function, and a function is given with the help of this table. Okay, let's try to make a graph out of it. So we have 4 states, S0, S1, S2, and S3. Okay, we will start in S2. And then from S2, we'll see what happens. So if we get an A in S2, we will go to S1. You see, if we get in S2 an A, we will go to S1. Okay, if we get a 1 in S2, we stay. So if we get a 1, we stay. And if we get a 2, we go to S0. So for state S2, all possible symbols which can enter the state machine or state automaton are defined and are given an output. Okay, then let's just check one by one all states. So let's look at this one, state S1. So in S1, if I get an A, then I go to S0. If I get in S1 a 1, I stay. And if in S1 I get a 2, I go to S2. Okay, S0. If I get an A in S0, then I go to S1. If I get a 1 in S0, I go to S2. And if I get a 2 in S0, I stay. Okay, only one left, S3. If I get an A in S3, I go to S0. If I get a 1 in S3, I go to S2. And if I get a 2 in S3, I also go to S2. So this is my complete graph corresponding with the FSA given by this definition. Okay, new subject for this lesson is quite a simple one. It's called a finite state machine. And in fact, that's just an FSA, but now it produces things. And the name machine is because it produces elements. So we get input, but we also produce output. We do an action, or we show something, or whatever. So if we look at a finite state machine, again, we need to have one entry point. And then when we are in this first state, whatever we get, the computer will know what to do. So in this case, we have an input alphabet of A and B, but we also need an output alphabet. And in this situation, the output alphabet is X and Y and Z. Look, we have a Z here. So the input alphabet is AB, the output alphabet is X, Y, Z. There are two states involved. And the difference with a finite state automaton is that it not checks whether the words are valid, but it'll just start producing when it gets input. So for instance, if I start with an A, if we look at this first string here, A, B, B, A, then this first A will produce an X. And we start here, we get an A, we produce an X. And we go to S1. And if we're in S1 and we get an A, we will produce a Z. And we stay in S1. Then we get a B. So in S1 we get a B, we produce a Y. and we go to S0. Okay, when we are in S0 and we get another B, we produce an X and we stay in S0. And then we get another A, we are in S0, we produce an X and we go to S1. And this will continue on and on. So an infinite state machine just keeps producing output, no matter how long the word will be. So a finite state machine has the following definitions. So we have an input alphabet, in this situation AB. We have possible states, S0, S1, S2. We have output symbols X, Y, and Z. There is an initial state given, and we have a function. And now we need, in fact, two functions. One function to tell us from what state we go if we get a symbol to what other state, and one function which defines the output when we have that specific transition. And that is normally shown in a state table where we have an state, an entry symbol, and then we have in this function a combined action, the state we go to, in this case S0, and the output we produce, in this case A. So every cell has a pair, the next state and the output symbol. So if we look at this finite state machine, then the input alphabet is 0, 1. The states we have are S1, S2, S0. The output alphabet is AB, initial state S0, and the two functions defined by the state table. Okay, let's see if we can draw this graph. So we have three states, S0, S1, and S2. Initial state is S0. If in S0 we get a 0, we produce an A and we stay in S0. So we stay in S0 with a 0 and we produce an A. So the symbol which makes us do the transition is placed at the beginning of the arrow, and somewhere in the middle we will place the output symbol. So we get an A as a symbol from the input alphabet, we produce an A and we stay in S0. If we get a 1, we go to state 1. So we get a 1, we produce an A and we go to state 1. If we are in S1 and we get a 0, we go to state 2 and we produce an A. And if we get a 1 in state 1, we stay and we produce an A. So last one, if we are in S2 and we get a 0, we go to S0. So we get a 0 and we produce an A. And if we're in S2 and we get a 1, then we stay. Oh no, we don't stay. We go to S1 with a 1 and we produce a B. So this is the graph corresponding with the finite state machine as defined by all the properties of M. Okay, so how can we use this finite state machine idea to build an application? Let's look at a very simple one, to add two binary numbers. So, if we want to add binary numbers, let's give an example. Let's say we have these two binary numbers and we want to add them. Then of course we know we start on the right, we add 0 and 1, that gives us 1. We add 1 and 1, that gives us a 0, but I have to remember a 1 now. We have to carry a 1. Then we have 1 and 0 plus the carry will give us a 0 again, and we carry. And a carry plus 0, 0 gives us a 1, and then we have the 1. So to add those two binary numbers, we have this result. So how can we use our finite state machine ID to build an application? So let's look at the states we can be in. And hopefully you recognize that there can only be two states. I have a state carry and I have a state no carry. So when I begin, I don't carry anything, and if I have a carry, then I enter another state, a carry. Then there are several input possibilities. So my input alphabet could be I add two zeros, or I add a 0 and a 1, or a 1 and a 0, or a 1 and a 1. The output is in fact just a 0 or a 1. So the input alphabet contains 4 symbols and the output contains 2 symbols. Okay, so let's remember this one. We have 2 states, no carry carry, 4 input parameters and 2 output parameters. Let me erase this. Okay, so we had 2 states. We have a carry state, let's call it a carry, and we have a no carry state. Okay, in which state do we enter? Well, of course, if we didn't add anything yet, then we don't have to carry. So we start here. And then we could have 4 combinations. So we had the combination 0 plus 0. That just shortcut it to 0, 0, 0 plus 1, 1 plus 0, and 1, 1. Okay, let's start with 0, 0. If we get 0, 0, yeah, of course, we don't carry, but we keep in the same state. And so if we get a 0, 0, that means I produce a 0 and I don't need to carry anything. So I stay here. If I get a 0, 1, okay, that's also quite simple. I can just produce a 1 with a 0, 1 and I stay in the no carry state. And you can imagine that we do exactly the same for the 1, 0. And so 1 plus 0 in a no carry state will produce a 1 and will stay in the same state. Okay, the only special one is the 1 plus 1. So if I don't carry anything yet and I get a 1 plus 1, then I will produce a 0, but I need to carry. So as soon as I can, I have to use this carry to be used in an adding. So I produce a 0, but I go to the carry state. Now, in this carry state, if I get a 0, 0, okay, I was carrying something, so I need to produce a 1. But do I still stay in the same state or not? Well, let's think about it. So I have a carry and I get the input 0 plus 0. Okay, that means that I can safely produce a 1 and go back to the no carry state. So with a 0, 0 combination, I produce and I go back. If I have a 0, 1 or a 1, 0, then I got a carry and I still have a carry. 1, 0 plus 1 gives me a 0 plus a carry. So the output will be a 0 and I stay carrying. And I have 1 left. So if I get the input symbol 1, 1 and I had a carry, then 1 plus 1 plus 1 in fact makes 1 again. But I keep carrying, so I keep in this state. So now I've made a finite state machine, which can be easily implemented by a computer by just following orders. So we start at position, and whatever we get as an input, we follow the prescription. We produce the output. Okay, I hope this gave you a nice example of the usefulness of a finite state machine. And again, as stated already at the beginning of this MATH2 module, you will see a lot of more of these finite state machines when you're going to go and for object-oriented development, because in your designs they will be rather useful. Okay, this is the end of lesson 5, the languages part. If you have any questions, please feel free to post them on Teams or ask them in the next Teams meeting.